Alright, how's it going out there? This video will be about the algebra of quadratic functions. So our objectives for the video, pretty straightforward. I just want to define what's called the standard form. If you look in a textbook, this is what they'll call it. But really, the names aren't so important. What's important is the ideas. So I'll talk about the ideas behind the standard form. In particular, I'll talk about how the algebra of this form of the function for quadratics really builds off the algebra of linear functions. Okay, so quadratics really do build off of linears, and I'll talk a little bit about how we can see the structure of the pattern from the algebra. So remember, algebra is a language, and it's a language used to describe patterns. And so we should be able to, when we look at an algebraic expression, we should be able to understand some of what pattern it's trying to capture just by looking at the form of it. So that's what we'll do here, and let's jump right in. Okay, as a quick recap with linear patterns, right? You might have something like I've represented a linear pattern here with these smiley faces. So initially there are 2 smiley faces, then 3 more get added, then 3 more get added, and it's a very simple pattern where each time the figure goes up by 1, the number of smileys go up by 3. I've been calling that the rate of change. It's telling you how quickly the pattern changes. In a past class, you might have called that the slope, and that's appropriate for when you're graphing these things, but we're not graphing them here. Okay, so just rate of change is telling you how quickly the pattern's changing. In this case, it goes up by 3 every time. And then remember this blue box, right? The yellow box gives you the rate of change, whatever number goes in there. So in this case, the number would be 3 to put in the yellow box. And the blue box, what number you put in this blue box is the initial condition. So that would be 2, because initially at figure 0, there are 2 smileys, right? And so there's 2 pieces of information that a linear function has. And that's exact, so 2 numbers you have to put in these boxes, and that's exactly because there's only 2 pieces of information you need to make a linear pattern. Just tell me how much to start with and tell me the rate of change, and that tells you everything you need to know about the pattern. Okay? So we saw in a previous video then how quadratic patterns, just the number patterns, really build off of those linear patterns. So you need to understand the linears first, and then you can make better sense of the quadratics. Okay, so here's a quick example. This blue number pattern here is a quadratic pattern. Okay, so first of all, clearly the blue pattern is not linear because it's not increasing by the same amount each time. Okay, how do I know it's quadratic? Well, I take its rate of change. In other words, I look at how much it does go up by each time, like what these gaps are, and I look at that pattern. Okay, so when I do that, from 2 to 5 it goes up by 3, 5 to 10 it goes up by 5, 10 to 17 it goes up by 7, and so on, and I get this rate of change pattern down here. Well, this is a nice simple linear pattern. It goes up by 2 each time. So this is just a recap. Remember what it means for a number pattern to be quadratic. So if you need to go back and watch that video, go back and watch it. Okay. So these are the types of patterns, and now as I said in the start of the video, the algebra should reflect that. So because quadratic number patterns build on top of linear number patterns, it must be the case that the algebra of quadratic functions builds on the algebra of linear functions, right? So always start with the number sense. Almost all of algebra is just coding the rules, the number sense. It's coding the rules of numbers, right, into this little language, this concise little language. Okay, so this is the point. Since the numbers, the quadratic number patterns build off of the linear number patterns, we'll see that the algebra builds off of the algebra. The algebra of quadratics builds off the algebra of linears, and here I've represented it. So on the top we have a model. So this function will model quadratic number patterns. Notice that there are actually 3 pieces of information that you need, or in other words, 3 numbers that you need to put in these boxes to make your quadratic function. Okay, this is compared to the linear, which only has the 2 pieces of information. Now notice 2 of the pieces of information are the same in the linear and the quadratic. In the linear we have this yellow box next to an x, and in the quadratic we have the yellow box with the x, and we have this blue box at the end, the initial condition, right? So the new thing about a quadratic is that it adds on this x squared term, and as you'll recall from the last video, quadratic, quad means 4, squares have 4 sides, so quadratic patterns should be capturing the area of rectangles or squares, and that's why this x squared term gets added here, because that's exactly what's going on. Okay, so 3 pieces of info for a quadratic, 2 pieces of info for a linear, and I've summarized it here. What you want to look at is you want to think about each of these parts of the model as telling you something different about the pattern. The blue box tells you this sort of constant term, this initial condition. The yellow box, when it's just a linear, we said this is just the rate of change. But when it's a quadratic, there's really 2 components to the rate of change. There's the yellow box, which still tells you how fast the linear piece of the pattern is changing. And there's the green box, which is telling you how fast the squared piece of the pattern is changing, right? So again, quadratics build off linears. They still have the linear stuff in them, but they have this added area of a square piece over here in green. Okay, so we have the 2 different now rate of changes. The green box is telling me how fast the squared part is changing. The yellow box is telling me how fast the linear part is changing. And the blue box is just this constant part of the pattern. This is the part of the pattern that never changes, right? That's what it means to be constant. All right, so let's look at an example here. This is sort of the fundamental example to know. This is y equals x squared, and I've represented it as a visual pattern up here. So remember, x squared is just telling you the area of a square with side length x, and we see that's exactly what's being represented in this visual pattern. Right, on figure 2, there's a 2 by 2 square, which has area 2 times 2, or 2 squared, which is 4. Figure 3, 3 by 3 square has area 9. And so you plug in the figure number, you square it, and that tells you the area out. Now, you might be saying, well, hey, wait a minute. We were talking about quadratic patterns having 3 pieces of information. What happened to that? So I just wanted to point out here that there really, even if you write it as y equals x squared, there really are 3 pieces of information. The first piece, remember the rate of change of the squared part, well in this case it's just a 1, because what we're saying is that this pattern is just the x squared pattern. So I'm just taking sort of one whole square, if you like, and I'm updating that pattern as we go. Okay, so I have this one piece of the x squared part. That's why the whole visual pattern is squares. How much of this pattern is linear, is changing linearly? Well, nothing. There's not any component of this pattern that changes like a line. And how much of this pattern is constant? In other words, is there something that's not changing? And the answer is no. We're always growing like the area of a square. So really you just say, there's 0 linear parts to this pattern and there's 0 constant parts to this pattern. The whole thing is just the squared piece. Okay? So typically people don't write 1x squared, they just write x squared, and they don't write 0x, they just don't write anything, because 0 times anything is 0, right? And plus 0, they don't write this plus 0 here. But I wanted to point out that even when you're looking at this pattern, there really are 3 pieces of information. You're saying, I am taking the full x squared pattern, I'm taking 0 parts of a linear pattern, and I'm taking 0 parts of a constant pattern. Okay? So let's look at now another example that's a little bit different but still similar. Say I put now a 1/2 in front of my x squared. Well, a lot like the last pattern, there's 0 linear pieces and 0 constant pieces in this pattern. There is this 1/2 though, and now I've kind of color coded here, right? So now what I'm going to be doing is I'm going to be taking half of the squared patterns, and I've represented this by these little triangles, right? If you take that x squared pattern, which was the full boxes, and you cut it in half, you get these little triangles. Okay? So when I read this off, again, people don't write the 0x and the plus 0. They just put the 1/2 x squared part. But you can connect now the visual, like what the pattern is doing, to the algebra. The algebra says you're taking half of this squared pattern. Okay? All right, let's look at one where we have multiple components. Let's say I do x squared plus 2x. So now if I break this down again into my 3 pieces of information, how much of a squared pattern there is, how much of a linear pattern there is, and how much of a constant pattern, I see my green box, that's a 1. I still have a 1x squared. Okay, so I should see some squares in there. I have a 2 times x, which tells me I should see this yellow box. I should see something that's growing linearly with a rate of change of 2. So here we have the linear part of the pattern is growing at a rate of change of 2, and the quadratic, the squared part, is growing at a rate of change of 1. And again, I have 0 constant pieces. Now I've represented the pattern visually, again, as a visual pattern up here. You might be looking at this pattern saying, well, how do I see in this pattern? Like in the last patterns, I could see very clearly where the squares were, right? How do I see the 2 components in this pattern? And so I went ahead and I colored this in for you. I color-coded it. If you just look at the green part of the pattern, you will see the green squares. There's a 1 by 1 square in the first figure, a 2 by 2 in the second, a 3 by 3 in the third, and a 4 by 4 in the fourth. So that is this 1x squared part in green. It's telling you do the square part of the pattern. Where does the 2 come in, the yellow 2? Well, this is the linear part. And if I just look at the yellow, the boxes that are shaded yellow, and I look at that pattern, it goes 2, 4, 6, 8, and so on, right, to 10 to 12. That's the yellow pieces on their own make a linear pattern, right, with rate of change 2. Each time there are 2 more yellow boxes than there were before, right? Here I had 2, here I had 4 yellow boxes, and here I had 6, okay? Is there any part of this pattern that's constant, that's not changing, that's always just kind of hanging around? The answer is no. I can see that the pattern fits nicely into the green squared piece and the yellow linear piece. All right, so that's going to be kind of your objective as you get more familiar with quadratic functions, to be able to read off from the algebra what it's telling you, what type of pattern it's representing. All right, so in summary, quadratics build on linears. The rate of change of a quadratic pattern is a linear pattern. That's just with the number patterns. So then we would hope that the algebra of quadratics would also build on the algebra of linears, and it does. We get what's called the standard form. Again, that's not super important that you know that verbiage, standard form, but this is what they might call it in a book. You get the standard form where we see the 3 pieces of information, and in fact we see the linear parts of the pattern here, right? So if you have a quadratic that does have some linear pieces, they'll be represented by this yellow and blue box, but the squared part of the pattern is represented in this green box. Okay, so you should be able to see what the 3 numbers represent, and again, repeating myself now, but they're telling you how much of each type of pattern, right? A 1 in the green box means you're taking the full x squared, or a half means you're taking half of the square. A 2 in the yellow box meant we're taking twice a linear pattern with rate of change 2. Okay, so that's what we got. Thanks for listening.